Dear friends, welcome to another very exciting edition of Data Science Tutorials. Myself, Dr. Suptik Mukherjee. Today's topic is linear regression model, and we'll implement it on house prices in London. Now, before we go to the topic, I have a small request. Please don't forget to subscribe our channel. We put a lot of hard work and effort in creating these videos. If you subscribe, it will motivate us significantly. Also, we are going to start courses on data science from the 1st of November. Those interested can email me. The email is given in the description below. Also, the notebook that we are going to use today, including the code, will be available in the GitHub repository, and the link for which will be provided in the description. So now moving on to the topic. Linear regression models on house prices in London. So first of all, what is regression? Regression is a statistical technique and is used in machine learning and statistics to model the relationship between a dependent variable and a independent variable. So the dependent variable is known as target and the independent variable is known as features. Now, to give you a simple idea about where we are going, suppose I have a data set and the data set is london.csv. So when I read the data set, I want to know the price for the area of the houses. Okay, so I have houses which are certain carpet area, and this is in square feet, and I want to know the price corresponding to it. So I want to predict the price for a certain area. So which is the independent variable here? So the area can change, so that is a independent variable, and price is based on that, so that's a dependent variable. Okay, and we are looking for a linear regression, so we want to get to something like y is equal to a plus bx. You are all familiar with this equation, and it's the equation of a straight line, and this is the slope, this is the intercept, and this is the independent or feature variable, dependent or target variable. Now when I plot this line, this is my x, this is my y, and this is the intercept, and I should get the slope. Now when I try to implement the linear regression model, there are certain things that will help us understand how good the fitting of the model has happened, like r square, and then mean square error, and root mean square error. Now how the model works, you have to understand that how the fundamentals of the model work. Now so this is my this is the x-axis, this is my x, and this is my y. So and this is my fitted line. So suppose I take a point, this is my actual target, which means that this is the actual point that I have. And this is my predicted target on the line, right? So the what is the error? This is the difference between them is the error. Now once I what I'm trying to do, I am trying to fit a line which minimizes this error. Okay, so what do I do to do that, to achieve that? So to achieve that, let's say I have a mean square error, which is basically the sum of all the errors, which is yi minus yi hat. So yi hat is the predicted target value, as we can see here, and yi is the actual target. So this is one error, there will be many such other points here, and I get all the errors and then square it. Why I square it? Because it doesn't matter to me that if it is a positive or negative, all the value of that error I am trying to minimize. Okay, so I square it and then I divide it by the number of points. Okay, now if I replace the value of yi, which is this is my yi, right, the actual target, and I get what is yi is a plus bx. Okay, so I can call it instead of a, beta naught plus beta 1 x. And say if I have, instead of just one feature, if I have many features, so I can have beta 2x plus beta 3x and so on, right? And then the minus yi, which is the predicted target, right? So this whole thing is the cost function, right? So I am trying to minimize the cost function. So minimize the cost function here in linear regression. We seek to minimize the MSE, the mean square error, by adjusting the coefficients beta naught, beta 1 and beta 2. So in other words, I need to adjust this coefficient to minimize this error. Now, how do I adjust the coefficients? I adjust the coefficients using something called the gradient descent, right? So the gradient descent, what it is doing is, so I am using partial differential equations to minimize. So you have the MSE, the mean square error, and if you and the mean square error is a function of these beta naught, beta 1, beta 2 and beta 3, right? It contains all these terms. So if I do a partial differential equation, a partial derivative of the mean square error, and the partial derivative of mean square error with respect to b naught, with b1 and b2, and so suppose I do with it, say bi. So what is going to be the so beta I? So beta I new is beta I old minus the partial derivative of MSE with respect to beta I old, right? And you have another term alpha. Alpha is basically the learning rate. Learning rate means if I have the if I have the model in such a way that the gradient descent is going to be very steep. In other words, if the it's very varying much from the line, the actual values, the actual features, then what's going to happen is that alpha is going to be very large. While if it is these numbers, actual numbers are very close to the fitted line, then alpha is going to be small but going to be more accurate. In other previous case, it was less accurate, right? So that's how I get the gradient descent. And so eventually, what we are doing is we are going to um, minimize this MSE. When we minimize the MSE, that's when we get the fitted line, which where the actual target values will be close to the predicted target. How well we have got it? We have to use these values like this r square and mean square error, root mean square error, to determine how well this fitted line is close to the actual value. Okay, so let's start the coding, um, and we'll go through all the things that we discussed in the coding. Okay, now coming to the uh, code. First, we have a data set which is london.csv, and we use the first we import the libraries. We import NumPy, we import Pandas, we import Matplotlib for the plotting. We import from sklearn. We import the linear model for linear regression as linear regression, and from sklearn matrices we import the mean square error, and we import the math library. So now first we read the file which is london.csv using the pandas and read underscore csv function, and then we use the head function to basically display the uh, features that we have. Now here, this is a supervised learning linear regression, because we have the features based on which are labeled, based on which we are determining the another value, right? So it's a supervised learning. Now I come to this later, but thing is, here first what we are trying to do is we have the data, which is the data frame that we have created out of reading this file, and transforming the file into data frame, and then in that data frame data, the area in square feet is my features, the price is my target, right? And then what we do is I have an array which transforms uh, the features into a two-dimensional array, which is going to be my x. And similarly, the target variable will be transformed into two-dimensional array. And I show you what it means. It means that if I have my features like this, then after using this code, np.array features and reshape, I get a two-dimensional array like this, which is fit for machine learning. Okay, now and I have printed this, and I'll show you how after the code is run, how it looks like. You see, this is my two-dimensional array, and this is my np.array target. So that's what I'm printing it through the code here. Okay, now I train the model on the data, so I use regressor.fit. So what regressor.fit is going to do is going to using the parameters x and y, it is going to fit the line, right? And the regressor comes from the linear regression model. And then so this is the regressor is basically instantiate a linear regression object. Okay, and is based on what? It is based on the residual sum of squares, the the mean square error, and so on. I have um, explained the theory before. So now we see how the mean square error is. Um, so the mean square error is using two parameters, y and regressor dot predict. Okay, so the mean square error, uh, if once I have the mean square error, I'm going to find the square root of it using the math library, and then square root of mean square error. Now, what it says basically, it is going to show me how closely these target variables, actual target variables, are to the fitted line, right? And the other thing that I need is r squared value. And as I explained before, the r square value, let me go to the r square. So because we need to explain this part a little bit more. So the r square value can have either 0 or 1. So 0 means that there is it does not explain the variance in the target variable and um, the fitted line, right? So r square is 0. R square is 1 means it perfectly explains all the variance in the target variable and the fitted line. So if r square is 1 minus ssr by sst, so what is ssr? ssr is ssr is sum of squared, the squared residuals, sum of squared residuals, ssr, and that means the target variable minus the predicted target variable. If I square this and sum it up, then that's ssr, and the sum of square total is target variable minus mean, and if I square it and this total take the total sum, that is my sst. So 1 minus ssr by sst is r square, right? And so the what the code is doing here, um, so the code extracts all the features, and then the code calculates the mean square error and r values, retrieves the model coefficient, slope, and intercept, and visualizes the data with the regression line, right? So here, as I was mentioning before, so first we get the MSC, the RS, the root mean square error, and the R squared as regressor dot score, and x and y are the parameters. And then I find the slope, which is regression dot coefficient. And what is coefficient? What is 0, 0 is? The 0, 0 refers to the first dimension of the coefficient matrix. So it's a matrix where 0 is the first dimension, and then the 0 following the first 0 is an indexing a specific coefficient within the first dimension. So that will give me the slope, and the slope is basically, is going back all the way. This is what I'm trying to find out, b, or here if you say is I'm trying to find beta 1, right? Beta 1 I'm trying to find. Okay, so that's my slope, and then that's how I can get it, the slope. And then the intercept, how do I get it, the which is when x is 0, what is the y value, right? That's my intercept. And intercept 0 at the end of the regressor is used to extract the first element of the intercept, because in linear regression there's only one intercept value, so you are simply extracting that single value, right? And then I um, make predictions. I use this array where this value is 4000, and I predict the value, the price for the new size. Okay, and so that's how I predict the price based on the size, 4000 square feet. Okay, and then I have to visualize the data. I have I use a scatter plot with x and y, and then I plot with the x and regressor.predict, um, and so regressor.predict x is going to give me the fitted line, and then the title linear regression is a level area, x-axis level, and y-axis level is the price, and I show the plot. Okay, so what I have is I have rsme, the r square, and I print out the rsme, I print out the r square, and the slope, the intercept, and the predicted price. So with all that, you can see here that this is my linear regression model, this is my fitted line, and these are my various actual target variables. Okay, so that's all about linear regression. Thanks, friend, and we'll have another lesson on regression soon. Please do subscribe. Thanks for watching, and happy learning.